Hello there, young scientists. Ever wondered why honey flows so slowly compared to water, or why ketchup sometimes just refuses to move unless you smack the bottle? Well, that sticky, slow flow is all about a special fluid property called viscosity. Imagine viscosity as the internal friction inside a fluid. It's what resists layers of the fluid from sliding past one another smoothly. When different layers in a fluid try to move at different speeds, they rub against each other, just like trying to slide one book over another on a table.
Now, when a fluid flows over a solid surface, the layer right against the surface tends to stick because of adhesion, kind of like glue. Meanwhile, the next layer glides over that, creating a kind of shear or sliding force between them. This idea is captured beautifully in Newton's law of viscosity, which tells us that the force needed to keep these layers moving relative to each other equals the viscosity times the area of the surface times the velocity gradient, which means how quickly the speed changes from one layer to the next. To put it simply, force equals the Greek letter eta, which stands for viscosity, multiplied by area and multiplied by the rate of velocity change with distance. And just so you know, fluids that follow this neat, straight-line relationship between force and velocity gradient are called Newtonian fluids, like water or air. But fluids like blood or toothpaste don't play by these rules and are called non-Newtonian. So next time your toothpaste squirts out differently depending on how hard you press, you'll know it's all viscosity at work. All right, let's take a closer look at what keeps those fluid layers moving steadily past each other. To maintain a smooth, steady, layered or laminar flow, the force you must apply is directly proportional to how quickly the velocity changes across the layers. That is, the velocity gradient. This relationship can be written as force per area equals viscosity times velocity gradient. In other words, shear stress equals viscosity times the velocity gradient. The unit we use for viscosity in the international system is the Pascal second, which might sound fancy, but it's just a Newton second per square meter if you want to get technical. Dimensionally, viscosity combines mass, length, and time, as mass times length to the -1 over time. Quite a mouthful, but it just tells us how these big ideas fit together physically. Now, what exactly is this velocity gradient? Imagine fluid layers stacked like pancake batter. The top layers move faster and the bottom ones slower, so velocity changes with depth. In liquids, viscosity mainly results from the cohesive forces, those tiny molecular attractions holding molecules together. But in gases, viscosity comes mostly from molecules bumping into and diffusing among one another, almost like a busy bumper car ride on the microscopic scale. To picture this, imagine two flat plates with fluid in between. The top plate slides over with some velocity, the bottom one is still, and you see arrows showing force F pushing the top plate, velocity varying from 0 at the bottom to maximum at the top, and the distance between the plates as the change in x. This setup perfectly illustrates the velocity gradient and shear force in action. Now let's talk about how fluid particles move in what's called streamline, or laminar flow. Think of it like orderly traffic lanes in fluid form. In this smooth flow, tiny fluid particles at each point follow the same paths with a steady velocity, forming layers as parallel as slices of a loaf of bread. Because of viscosity, the speed of these adjacent layers differs, creating a velocity profile that changes from 0 at the boundary to a maximum right in the center of the flow. That 0 velocity at the wall is known as the no-slip condition. Basically, the fluid clings to the wall and refuses to move. Now imagine flow inside a cylindrical pipe. At the very center line, the fluid moves at the highest speed, and as you move radially toward the walls, the velocity decreases, creating a nice, smooth, parabolic curve when you plot velocity against the radius. This parabolic velocity profile is a classic signature of viscous laminar flow inside tubes and pipes, and shows how viscosity shapes the motion we see every time water flows through a tap, or blood courses through your veins. Picture a tiny sphere gently sinking through honey, or rising in oil. What slows it down and makes its motion steady? This situation is beautifully described by Stokes' law, which tells us that the viscous drag force on a sphere moving slowly in a fluid equals 6 times pi times viscosity, times the sphere's radius, times its velocity. In words, drag force equals 6 pi eta rv. When a sphere moves through a fluid, it feels three main forces: its weight pulling it down, the upthrust or buoyant force pushing it up, and the viscous drag resisting motion. After some time, the sphere reaches terminal velocity, the steady speed at which these forces balance perfectly, and it no longer accelerates. The terminal velocity can be calculated using the formula 2/9 times the square of the radius multiplied by the difference in densities of the sphere and the fluid, gravity, and divided by the viscosity. To be clear, Vt equals 2 divided by 9 times r squared times open bracket rho minus sigma close bracket times g divided by eta. Here, r is the sphere's radius, rho is its density, sigma is the fluid density, and eta is the viscosity. Remember, Stokes' law applies only when things are nice and slow, meaning the Reynolds number is less than 1. So for small spheres moving gently in continuous fluids, this law gives us a great way to predict motion. Now, have you noticed how syrup gets runnier when warmed, but air can feel thicker or thinner depending on temperature too? That's because viscosity changes with temperature. But interestingly, liquids and gases don't behave the same way. In liquids, viscosity decreases as temperature rises, because the molecules' sticky, cohesive forces weaken, making the layers slide past each other more easily. On the other hand, in gases, viscosity actually increases with temperature, because molecules move faster and collide more frequently, which enhances the transfer of momentum inside the gas. We can describe these changes using empirical equations. For gases, viscosity equals a reference, viscosity times E to the power of B over T, where B is a constant and T is temperature. For liquids, viscosity follows a similar formula, but with a minus sign exponent, eta equals eta, 0 times E to the power of minus T, the negative A over T, with A, again a constant. If you were to see plots of viscosity versus temperature, liquids would show a downward slope and gases an upward slope. This contrasting behavior is crucial for understanding and designing systems where temperature and fluid flow interact, like in engines or meteorology. Let's wrap up with a quick example problem on terminal velocity that brings all this theory to life. Suppose we have a steel sphere with radius 1 times 10 to the minus 3 meters, density 7,800 kilograms per cubic meter, falling through glycerin whose density is 1,260 kilograms per cubic meter, and viscosity is 1.5 Pascal seconds. Using standard gravity of 9.8 meters per second squared, we want to find the sphere's terminal velocity. We use the formula Vt equals 2/9 times r squared times open bracket rho minus sigma close bracket times g divided by eta. Substituting the values gives us 2 divided by 9 times open bracket, 1 times 10 to the minus 3 squared, close bracket times open bracket 7,800 minus 1,260, close bracket times 9.8 divided by 1.5. Crunching those numbers, the terminal velocity comes out to approximately 8.56 times 10 to the minus 3 meters per second. Wow, that's a tiny speed, confirming that the sphere moves very slowly and steadily, justifying our use of Stokes' law here. Let's quickly recap what we learned about viscosity today. First, the viscous force acting between fluid layers under shear flow is nicely described by force equals viscosity times area times velocity gradient. Next, the viscous drag force on a small sphere moving through a fluid slowly is given by 6 times pi times viscosity times radius times velocity. Then, the terminal velocity of such a sphere occurs when forces balance and is given by 2/9 times radius squared times the difference in densities times gravity divided by viscosity. We also saw that viscosity decreases with temperature in liquids, but increases in gases, showing opposite thermal behavior. Lastly, laminar flow features those layered motions with parabolic velocity profiles, a direct result of viscosity-induced shear. That's it for today's lesson. Remember, physics is always more fun when you can laugh and learn together. See you in the next session.